out. Tonight's lithograph is the Hubble Space Telescope. This is a picture from the last servicing mission. It's actually one of the farewell pictures. I look at this and I sort of get nostalgic because this is the last time humans visited Hubble. Okay, this is one of the last photographs as they were leaving. On the back is updated text, newly updated for this year, to include all of the new instruments and information about it. The previous version we had of this lithograph had some old instruments on there that actually got removed. So we have new text with an old picture. All right, and please pick them up on your way out. The reason we are doing that is because tonight we're talking about Hubble. We're talking about observing with Hubble from scientific idea to published result and everything in between. And Bill says he's going to do this in real time, so we'll be here for about 2.5 years. Upcoming on December, Mark Kamiankowski from Johns Hopkins will be talking about black holes and other dark matters. I don't know if that's his actual title because he said, I'll give this talk. And I said, well, why don't we call it this? And he said, okay, sure. He may change his title before then, but because that's the title. I gave it to him, but he seemed to like it. In January, we are not doing the first Tuesday. We are not doing the second Tuesday. We are doing the third Tuesday, okay? The first Tuesday is January 1st, New Year's Day. We're not going to do that. The second Tuesday is during the American Astronomical Society meeting. The January meeting is the biggest AAS meeting, astronomy meeting of the year. A lot of people will be in Seattle, including myself, for that meeting. So we're going to push back to January 15th. For initial exoplanet discoveries with TESS, the Transiting Exoplanet Survey Satellite. This is one you don't want to miss, okay? Because this is a brand new satellite, brand new results from it. And guess what? There's going to be a lot of discussion of this at the AAS, so there'll be a lot of new content that he can discuss during this talk that he couldn't discuss if we held it before the AAS, okay? So Scott Fleming will discuss that in January. And in February, Maya Mora-Martin will be talking about your place in the stars. Okay, if you would like more information, you can go to our website, use your favorite search engine for Hubble Public Lecture Series or Space Telescope Public Lecture Series. You'll find this web page where we have the upcoming lectures listed over here on the right. We have links to our webcasting, both on YouTube and the Space Telescope webcasting folks. And you can see the archive back to 2014 on YouTube and back to 2005 in our wonderful webcasting sites. You can also sign up for our email list and get like 2 emails a month about what the upcoming lectures are going to be and when they are, which will help remind you that it's going to be the third Tuesday and not the first or second Tuesday in January. So the announcements, sign up to the website. If you have questions, there's email address publiclecture@stsci.edu. You want to follow us on social media, we got Facebook and Twitter and YouTube and Instagram for Hubble, for the Space Telescope Science Institute, and for the Webb Telescope as well. I have a little bit that I do. I don't do much. Unfortunately, the clouds are out tonight and the Maryland Space Grant Observatory will not be operating. They do have open houses on Friday evenings. I'm not sure what the weather forecast is for this Friday. I understand that they're doing a special event on the roof of Bloomberg this weekend, something called Celestial Terrestrial, and I couldn't find a web link for it. But the folks who run the Space Grant Observatory told me that this weekend, if you can find something about Celestial Terrestrial, they're doing it on the go up on the roof of Bloomberg, and it has some art component as well as a science component to it. And Zolt up there is looking at it because he has an art exhibit called Celestial Terrestrial Convergence that he has done, and this is not Zolt LeVay's art convergence art show. Okay, all right. Now our news from the universe for what question? The Bloomberg building is right across the street, that big, huge brick building, that edifice that rises across the street from us, okay? That is where the physics and astronomy departments are housed, okay? Now, our news from the universe for November 2018. Our first story tonight are some mission updates. If you've been paying attention, there's been a lot to pay attention to over the last month or so. Okay, first of all, on October 5th, our favorite telescope, the Hubble Space Telescope, went into what we call safe mode because we had a failure of one of the gyroscopes. Now, this gyroscope had been showing anomalies for about a year, and we were sort of expecting it to fail at any time, and it did fail on October 5th. And we have, of course, procedures built in place because we have 6 gyroscopes on Hubble, and we need 3 to point it accurately. When they fired up one of the reserve gyros, it had a problem. Its high spin rate was too high. Its low spin rate was not within observational parameters. So they did some testing, and they couldn't solve it. So they did more testing. And it sort of went somewhere, but not quite where they wanted it to. So yet they did even more extensive testing. These guys are really, really good. They're very patient. And after almost 3 weeks, they were able to find a solution to the problem and get that reserve gyro back into observational status. Okay, so the pointing of that gyro was high quality enough that we could do Hubble observing. So on October 26th, we resumed observations. Okay, so Hubble took a 3-week vacation from its observing mode, while of course the engineers here on the ground took anything but a 3-week vacation getting it back in. They do an amazing amount of work. Also, the Kepler mission had a problem. It had done its primary mission for 4 years, which were observing stars and looking for the light dips that indicate planets passing in front of them. That's called the transit method of looking for extrasolar planets. And then it had a reaction wheel problem. This was a while ago. And then we moved it to its secondary mission, the K2 mission, which it did observing as it could, given the reaction wheel problem, for another 4 years. And then finally, on October 30th of this year, the fuel was exhausted. The pointing fuel, the fuel that's necessary to point the telescope, was finally exhausted, which was, again, what was expected. And so that the the Kepler mission had to be brought to a close. But it did do its full 4 years of its primary mission, and it got another 4 years of its secondary mission. It was actually up for almost 9 years doing observations. Is that the end of Kepler? No, because Kepler created an incredible data set of light curves, all of these stars and their brightnesses and their dips in their brightnesses that will be researched for quite some time to come. And where are you going to go for that? You're going to go to the Mikulski Archive for Space Telescopes right here in this building, also affectionately known as MAST. And one of the managers of it is sitting right up there, who retired a month ago. I forget what your status was with what your title was on MAST. Archive Sciences Branch Manager. That's Karen LeVay. Zolt and Karen both retired a while ago. And so the MAST archive here will continue to serve data for the Kepler mission. And so it will actually have a lot more science results to come, because one of the things that we're getting in the modern era is you get this incredible data that people will search through the archives and make new discoveries for years and decades to come. The third mission update it concerns the Dawn mission. And if you remember, the Dawn mission was to study the 2 largest asteroids, Vesta and Ceres. It was launched in 2007, spent 4 years traveling the solar system to get to Vesta. It stayed with Vesta for a year, and then continued on traveling 3 years around the solar system to get to Ceres. Spent the last 3 years studying Ceres in a orbit, a very close orbit. Amazing data about Ceres. But a day after that the Kepler mission fuel was exhausted, it was announced that the Dawn mission fuel was also exhausted. Neither of these were any surprise, okay? We knew that the hydrazine only lasts for so long for pointing the telescope. But Dawn celebrated 11 years and 4.3 billion miles around the solar system. So the Kepler and Dawn missions are finished. Hubble is back in operation, and those are your mission updates. Yes? Parker Solar Probe. I have not mentioned the Parker Solar Probe. You want me to mention it next month? I will read up about the Parker Solar Probe. It did make a very close pass to the sun over the last month or so. It's got to make lots of things, and it's still accumulating data. They're not going to be announcing results from it. I usually chime in when there are results announced, but just for you, I'll take a look at the Parker Solar Probe for next month's news. Okay. All right. So for some science results tonight, we have evidence of an exomoon. Okay. So we have seen lots of planets, or evidence of lots of planets around other stars. These are called extrasolar planets or exoplanets, okay? But we have never seen one with a moon. And with the Kepler data that I mentioned just previously and some Hubble follow-up observations, we now have evidence that there may be a moon around a star called Kepler 1625 and a planet called 1625b. All right, so the way it works is that, as I said, Kepler records the light of the star and the dips in the light when a planet passes in front of it. And with this massive Kepler database, researchers up at Columbia University went searching to see if they could find evidence of moons. Right? So you've got a planet passing in front. If there's another moon, there would be another dip. And so they went through lots of these light curves looking for anomalies that might indicate a moon. They found about 40 candidates, but this was the best one. And because this was the best one, they were able to get Hubble follow-up time. And so they used Hubble follow-up time to record the light curve really accurately. And Hubble saw the planet passing across, as you see in slide 2. And then the planet stops, the planet comes out of transit in slide 3. And then in slide 4, you can see a moon passing across, which causes another much smaller dip in the light curve. Now, unfortunately, the Hubble observing window closed before the moon made its full pass across, so they can't fully confirm it, okay? They would need actually to look many times over and over again, so they're proposing, of course, to do follow-up observations. But if confirmed, this is the first detection of a moon around a planet around another star. And that would be kind of cool. Not only is it interesting for that, but also because it's not, what color is that? Does that look like our moon? This is not a moon like our moon. This is not a moon like any moon in our solar system. There are 200 moons in our solar system. None of them are like this because this is actually more like Neptune. Okay? The planet is several times larger than Jupiter, like 3 to 5 Jupiter mass planet. And the moon is like a Neptune mass planet. All right? And we do have one moon in the solar system that has an atmosphere, Titan. But it's at its core, it's more like a rocky planet. Okay? An Earth, Venus, Mars type planet, right? This is a planet like Neptune and Uranus, but it's a moon around a planet that's larger than Jupiter. Yeah. How do you form a Uranus-type planet around a Jupiter-type planet? A Uranus-type moon around a Jupiter-type planet. I can't even say Uranus-type moon because it just doesn't work in my brain. It probably didn't form in situ according to our current ideas, but maybe we don't have the best ideas, okay? So this is intriguing, not only because it could be the first moon discovered elsewhere in the universe, but also it might be the first giant moon discovered in the universe. So stay tuned. There might be more coming up. All right? Any chances of binary planet? No, the mass ratio between the planet and the moon is approximately the same as the mass ratio between Earth and our moon. So it's relatively large. Actually, I think it's larger than the mass ratio. I think it's only the moon is only a few percent the mass of the planet. Okay, so that wouldn't qualify as a binary. Good question though. Thank you. All right, one last thing to note is Hubble is having its symphonic premiere. This is a project I'm very happy to tell you about. We've been working on it for 18 months. On this Friday, at the Kennedy Space Center in Florida, we'll have a premiere of Deep Field, The Impossible Magnitude of Our Universe. This is a project we've been working with conductor and composer Eric Whitaker. He composed a 23-minute symphony called Deep Field, which was inspired by the Hubble Deep Field. And we have been working with his company, Music Productions Limited, as well as 59 Productions, a company based out of London, to create a film to go along with his symphony. And it will premiere Friday, November 16th, down at Kennedy. It will also be released on YouTube. Okay, so everyone can see this. It's a how to describe it? It's a modern, somewhat minimalist symphony with very stirring music and very quiet music. And the progression of images starts with our very own Zolt LeVay's photography of the Milky Way in what national park? Capitol Reef. I want to say Canyonlands, but Capitol Reef. He was a photographer. He was out doing an artist in residence at Capitol Reef National Park and got an amazing shot of the Milky Way panning across the night sky. That opens the film. We go through planets and stars and nebulae and galaxies and out to the edge of the universe and the deep field. In this, with all to Eric Whitaker's wonderful music. So look for that. If you want more information, you can go to deepfieldfilm.com. It says it will be released globally 7 a.m. Eastern Time on Friday. Yeah. The charter review? Can we all go? Yeah. And I will probably take one of the public lecture series next year and play this film for you, and we'll do a discussion of what we did. The Space Telescope Science Institute was involved in 11 sequences in this film. Over half of the visuals are derived from our work, so we're very, very proud to show this off to the public. All right. And now our featured speaker. Let's switch over to his slides.
Dark matter.
Our speaker tonight is Dr. Bill Blair. He's across the street at Johns Hopkins, but he's also here at Space Telescope in a way. He joined Hopkins in 1984 and has been there ever since, working on the Hopkins Ultraviolet Telescope, which twice flew on the space shuttle, observing in ultraviolet, which you can only do from space. Then he worked on an even more ambitious ultraviolet telescope, the Far Ultraviolet Spectrographic Explorer, FUSE, and he parlayed the experience of running FUSE to come over and work with us on the James Webb Space Telescope, where you can see he is project scientist for user support for JWST. So he's going to use that amazing knowledge to tell us all about Hubble. And ladies and gentlemen, Dr. Bill Blair. Thank you.
Thanks, Frank, and thank you all for coming out tonight. This is great to see such a good crowd. So I am an astronomer. I've used Hubble many times over the years, not as many times as I would have liked to, but I get lucky every once in a while and get a project. The functional side of my work, though, has always been in user support, and user support is supporting astronomers to use the various facilities like the Hubble telescope or like the FUSE or the Hutt telescopes before that. And so a lot of my professional activity has been involved in enabling science, the systems and the software to help run these telescopes and get the data that astronomers need or desire. So I'm going to put those two pieces together today, and my intent is to try to give you a little bit of a behind-the-scenes look at what it takes to get a project accepted for one of these telescopes, to get it scheduled, to get the data back, and to do something reasonable with the data after it comes back. I think you'll get a perspective on why it takes an institute like this to actually run something like the Hubble Space Telescope, because there is so much involved behind the scenes. So I know that you all have seen many of these wonderful pictures that are released occasionally, either in press releases or in photo releases from the Institute. Of course, the Hubble Heritage Program for many years put one out every month. This is just a partial screenshot of the Hubble Heritage site, and you can see the many different kinds of pictures that are released. But behind every one of these pictures is a story. And the story usually has started with an idea, a question that needs to be answered, or an observation that can help answer a question, a proposal written by an astronomer, or more often a group of astronomers that wants to get the data to do that project, and then all the things that have to happen to actually schedule the telescope and to get the data, to archive it, and then back to the astronomer for the analysis and understanding part, and ultimately then a publication of a scientific result. And sometimes, fairly often, there's a pretty picture that comes out of that as well that the OPO group here puts out as a photo release, as you see here. And so tonight, this is going to be the story of one such picture. This one of M83, this wonderful galaxy that I'll be talking about off and on as we go through this process of what it takes to get science data from the Hubble telescope. So there's the full Heritage release. You see this marvelous picture, but there's what's going on here in this galaxy is that there's a very bright burst of star formation happening in the very center of the galaxy, the nucleus. You see these very well-formed spiral arms coming out. You see this brown stuff around here, which is interstellar dust bunnies, I like to call it, interstellar dust bunnies, running around out there in that galaxy. You see these big red glowing regions of hydrogen gas around the youngest stars that are forming, that are exciting that gas to glow. So you can see that there's a lot of star formation out here in the spiral arms, but there's a tremendous burst of star formation going on here in the center. And then this kind of yellowish red, hazy light that you see there are older stars that are yellower or redder in color, as opposed to the bright blue stars that have formed more recently. Well, that's a beautiful picture. It's a wonderful picture. And what does it take to even make a picture like that for a photo release? Well, in this particular case, it took two different programs of data. One here, the two yellow boxes were obtained first shortly after the Wide Field Camera 3 was installed in 2009. And the results from those two fields were so astounding that I was able to come along a year or so later and get a program to look at the red boxes here and a couple of other filters in the yellow boxes to complete this data set to observe M83. And I'll tell you a little bit about the science behind that as we go along tonight. I just thought I would point out that basically this first program was 16 HST orbits. My program was 36 HST orbits. That's 56 total, and at 14.5 orbits per day, you're looking at basically 4 days of Hubble observing time just to make this one photo release picture that you see here tonight. So here's a slightly different version of that same picture. And you can see that basically the photo release picture was the biggest rectangle you can cut out of this and not have this funny shape to it, but we got one additional field out here to get an outer spiral arm in this galaxy. And to put together this kind of a mosaic picture, it took some special work by some of the staff here at STScI, and of course Zolt here, who's here tonight. Great to see you, Zolt. Was responsible for putting together this photo release picture. I thought I would just mention, though, that this picture includes the filters that you see here in blue, which are all optical light pictures. There's 4 different bands of starlight in this picture. There were 2 more here. This lighter yellow is the infrared camera bands, and the H and K bands are not part of that picture, but were part of our data set. And then in the emission lines, you're seeing the H alpha, the red regions of diffuse gas in that picture. But we also took several other emission lines, including one here that was in the infrared that I'll mention briefly as we go along as well. Of course, Hubble mainly looks in the optical, but it goes into the ultraviolet and into the near infrared, which is difficult to observe from the ground. And these wonderful mosaics, after we stitched all this together, are actually available in the archive here at MAST. So why do we need to use Hubble to make an observation like that? I mean, we could take a picture of that whole galaxy with a ground-based telescope in one shot and not have to stitch all those fields together and whatnot. And the reason is there before you. There's nothing like having spatial resolution. This is a ground-based picture of just a little piece of a spiral arm in M83. It's a ground-based data set that we took down in Chile at the Magellan telescope. And this is an excellent ground-based data set. The seeing here is about a half an arc second. Now, if some of you amateur astronomers are out there, if you get below 1 arc second, you're doing well. Oftentimes, ground-based stuff is even not quite as good as 1 arc second. This is half arc second for the whole galaxy M83, but when you look at a little piece of it, that's what it looks like. And here are the same filters now used in the Hubble data, and if you're going to work on photometry of the stars, measuring the brightness and the colors of stars, I'd rather work on that data than on that data. And that's the motivation for getting Hubble time, is the spatial resolution. Well, what does it actually take then to get a proposal through the system here and have something happen? Well, it starts down here with an idea or a question that needs to be answered. After a lot of work, which I'll mention in passing as we go along, you submit a proposal. The proposal is peer-reviewed, and if you're lucky, you get accepted. And then you go into the planning and scheduling part of the process, which takes several months of work here at the Institute, as well as some more work by the astronomer to put together the detailed observing plan. It gets turned into a sequence of commands that get sent up to good old Hubble. If you're lucky, the data get captured appropriately, downlinked, and then processed and calibrated, which is a job that is also done here at the Institute and archived. And then finally, the data comes back to the scientist for scientific analysis and publication. So that's the process there, and I thought it might be fun to just look in a little bit more detail at this process, because in the simplest form of this, basically the astronomer is doing the work down below the line, and STScI does the work above the line. It's actually a little more complicated than that, but to first order, that's what's going on here. So let's look at this first part of the process. My idea, or anybody in the community, of course there's a lot of people writing proposals at the same time, write proposals and submit them to the Institute in what's called the Phase 1 proposal process. This peer review, so just to give you an idea, each of these steps along the way is a big job, and I'm skipping over a lot of details. Maybe I'll just pick out one here, which is the peer review. Imagine getting 1,200 proposals at the deadline for Hubble time, and having arranged ahead of time for about 120 scientists from around the country and around the world to come to Baltimore to participate in a review and a selection of these proposals. That's a lot of work. Travel, all the mechanics of arranging the rooms where these people meet, the effort that they go to, and the tracking of all the deliberations and so forth. That one box there is a huge job. And each one of these boxes is actually a pretty big job as we go along. But if we're accepted, okay, you go into that planning and scheduling phase. And here, each of these boxes can take maybe approximately a month to happen. The astronomer gets, of an accepted proposal, gets about a month to turn in the detailed proposal and maybe write a budget. There's a technical review process that happens here where that proposal is inspected by the experts here at the Institute to make sure that everything is up to snuff there. There's the construction of a year-long plan that takes all the observations that have been accepted and tries to figure out the most efficient way to do the observations throughout the course of the year. And kind of a rough layout, but basically what time of year for each observation. So your observation might get done all at once, or it might get spread up and broken up into pieces throughout the year, depending on what you're asking for. And then about 1 week at a time, a piece of this long-range plan is pulled into a short-term scheduling process where about 1 week of observations is put together into a sequence, literally a second-by-second sequence of what Hubble has to do. It gets turned into spacecraft language that Hubble can understand, and is then uplinked to Hubble, where Hubble operates autonomously then to make the observations. And if the target acquisitions work right and everything else works right, yay, you get some data out of that process. And so it's a long time coming, but that's the fun part when you get the data. After the data are captured on Hubble, they have to get down to the ground. They have to be calibrated and processed into a form that the astronomer can actually use, because there's a lot of engineering stuff in the background and whatnot, thermal temperature gradients that have to be accounted for, and distortions in images and so forth that get taken out as part of this process. That's a huge, huge process that involves hundreds of people here at the Institute to do, and to keep the pipeline up to date with the calibration files and so forth. And then the data gets archived, and the astronomer comes to the archive to get their data. And then the fun begins for the astronomer to actually do the science analysis and see what they can learn from the data. Okay, so for the M83 project, I wanted to just start with a kind of a big context picture here for a second, because this is a big scientific project to observe stellar evolution, star birth and star death in the local universe to determine how star formation is triggered, how it happens, how stars go through their lifetime, the impact that they have on their host galaxy. Those are all very large scale questions, and it would take a very large Hubble program to really address that. And so what happens is that people pick off a piece of that big picture and say, here's a piece I can actually tackle in a reasonable sized proposal. And for me, it was finding and studying the supernova remnants in M83. We also want to tie that into the stellar component as well, but my particular interest and motivation for this was to look at the supernova remnants in this galaxy, and it turns out that M83 is a particularly good spot to do this. M83 is about 15 million light years away, which sounds like a big number, but it's actually relatively nearby. Big face-on spiral galaxy. The starburst nucleus and lots of star formation going on even in the outer part of the galaxy. And the reason it's a good place to look for supernova remnants, the things that are left over after the supernova, the remnants of the supernova, is because it's had a lot of supernovae. It's had at least 6 or possibly 7 supernovae in the last 100 years. And so it's basically popping them off with great regularity. And so there will be of order then 60 or 70 young supernova remnants, say less than 1,000 years old, and many hundreds then that might be older still and still visible. So it's a great place to look for the supernova remnants that I want to find. This galaxy is about 1/4 of a degree across. If you know, the full moon is about 1/2 degree across, so if you could look up in the sky and see M83 like that, you'd see an extended physical object up there in the sky. It's a beautiful galaxy, although it is in the southern sky. Okay, so the idea in particular for me is to find the young supernova remnant population, and I'll tell you why here as we go along a little bit. But also, to tie the supernova remnants that we find to the nearby stars and say, can we actually determine something about the kind of star that exploded to create the supernova remnants that we see? And then the big picture stuff, then how does the entire population of supernova remnants actually impact the host galaxy? And to answer questions like that, you actually want to combine, let's say, Hubble data with data from the X-ray satellite Chandra X-ray Observatory, or maybe even the Spitzer Space Observatory for infrared data to put together the big picture there. Okay, so here's a couple of well-known young supernova remnants in our galaxy. The Crab Nebula, of course, a very famous object, almost 1,000 years old, and still expanding fairly rapidly. And the Cassiopeia A supernova remnant, which came from quite a massive star. And this is a picture actually with Spitzer data in red. The Hubble data is in yellow, and the green and blue are 2 different energies of X-rays from the Chandra X-ray Observatory. That tells you right off the bat that supernova remnants emit across the entire electromagnetic spectrum, and the part that we see with Hubble is just the optical or near-infrared light typically. But the Chandra data is also very interesting as well. Now these objects are nearby. We see lots of structure in them, and of course as we look way far away we don't see that kind of structure. But this is just 2 objects, and what's going on here, they're very different. This has got an active pulsar in here whipping around that's creating this blue haze in here of a synchrotron radiation. They're both expanding rapidly, but this one's expanding at 10 or 12,000 kilometers per second. This is at 1,800 kilometers per second. This one is enriched in helium and nitrogen and carbon. This one has oxygen, sulfur, argon, all the heavy elements. And is this typical? We don't know. We have 2 objects to look at, and we have all these parameters that are changing, and you'd really like to get a sample of young remnants that you could look at and try to understand some of the statistics of what's going on in young supernova remnants and determine whether these are oddball objects or whether they are kind of typical objects. They're often taken to be typical, and they're actually not. So by going to a galaxy like M83, big face-on galaxy, if we could find 60 or 70 young remnants here, that would be a big step forward, and that was part of my motivation for this. So I said that M83 has had 6 or 7 historical supernovae. Here's their positions in the galaxy here. I said 6 or 7 because this one here in red is actually one that we found as part of the survey that I'll tell you about here, the proposal that we wrote, that turns out to be a supernova that nobody saw. This is, I'm jumping ahead a little bit now because I'm showing you some results. Up here in this panel, we've got two ground-based pictures here. This is in emission lines, and this is starlight. And then here's the same filters then with Hubble, emission lines and the starlight of the same field of view. This is 1 arc second. We're looking at a tiny, tiny piece of M83 at this one little object here. And it was quite intriguing because it is so small. It's very small in size. And yet, when we took a spectrum of this object, this squiggly line here is what we call the spectrum in astronomy, and you see these big broad lines. That's just Doppler shifting of the emission lines in this picture, and it says that it's expanding at 5,200 kilometers per second. This is a young object. It's still flying out into space. And when you combine the expansion velocity and the upper limit on the size that comes from Hubble, it tells us that it has to be less than 100 years old. And yet the supernova was not observed. It could have just simply been that the supernova occurred when M83 was behind the sun, and by the time it came out, nobody noticed it. It had faded quite a bit and it wasn't noticeable. So it got missed. So I say there's been 7 supernovae, even though one of them wasn't observed. And that's actually a result that came out of the project that I'm talking about here tonight. So I think you can see the motivation here. The spatial resolution that Hubble provides is just astounding and crucial for the kind of project that I want to do. I want to measure the sizes of the supernova remnants that I find in M83 to find the smallest ones, which are the youngest ones, and then understand their characteristics relative to the X-rays or to other properties. And of course, I'm very interested in the other supernova remnants as well. So Hubble brings a lot to the table. The spatial resolution, of course, and helps you out in complicated regions where at ground-based resolution stuff would be smeared out with an H2 region nearby, a photoionized region, and it would make it hard to see the supernova remnant. I can see it with Hubble where I couldn't see it from the ground. And also the IR camera will come into play here in a moment because it lets us see through the dust and find supernova remnants that are hiding behind some of that brown dust that you saw in that first picture. So again, I'm jumping ahead a little bit here because this is data from the survey that I'm talking about here. Above again, these are ground-based pictures from the Magellan telescope. Here's the stars. These are the emission lines. And the things that show up kind of green and yellow or white here are the things that were identified as supernova remnants. So those 4 red circles. And here in the Hubble emission line data, you see the kind of greenish yellow shells. Here in 3 cases anyway, kind of an oddball object here that's a little bit different shape. But those 4 objects were supernova remnants that were identified from the ground, but they were characterized by the Hubble data and allows us to see what's going on. And you see I have a yellow circle here that doesn't seem to have anything defined in it, and that's because if I now look at the infrared image from Hubble, this is an iron 2 emission line image, and again you see these 4 objects that we saw before, but now you see there's also an object in the yellow circle that we didn't see. And if you look at the starlight, you can see that that yellow circle is projected onto a dark band of dust. That's a supernova remnant that is behind the dust, so it didn't show up in the optical, and we were able to find it with the iron 2 camera. So that's another thing that the Hubble wide field camera does for us. Okay, so I got to step back now. I'm already showing you data, but I haven't even gotten the proposal written yet, right? So we're going to go back and talk about the proposal. And there's a lot of work that goes into this. It typically takes about a month of effort, not only on the person taking the lead on the proposal, but the whole collaborative team. If you put together a team of scientists, we typically have several drafts of the science justification. We have to decide all this technical stuff about which instrument, which filters, how much time is needed, how does it lay out into orbits, because for Hubble I have to ask for a certain number of orbital viewing periods with Hubble. And then we have to, the important thing here is to write a clear science justification that tries to get the time through the peer review panel. And obviously then to submit the proposal. So just to give you a little flavor for this, this is one of the Hubble exposure time calculators, ETC. We love acronyms in NASA, right? So here's the ETCs. And you can see over here on the side that each instrument, the ACS, COS, the STS instrument, all have multiple exposure time calculators for their different observing modes. The one I've pulled up here is for the U.S.A, and this is just the first two steps of a 15-step process that you have to set for every calculation of every object that you want to observe to show that you're getting the right amount of observing time to give you a good signal-to-noise ratio in your data. And you can see the kind of things that you choose for imaging. You choose a filter. You set some detector parameters here. You say, do I want the exposure time needed to get to a certain signal-to-noise ratio, or I can select for 1,000 seconds or 900 seconds, what will the signal-to-noise ratio be? You can do it either way. And this goes down for about 3 or 4 more screens of information that you have to fill in for each calculation that you want to do with each observing mode or each filter. So it's a lot of work just to do that part to scope out how much time you need. Then when you've got your times, you put it into what's called the astronomer's proposal tool. And this is just one piece of that where I've already entered all the technical information into the proposal, and I've asked APT to lay it out into orbits for me so that I can see how it fits and whether it all works out. And so these blue speckled boxes are the observations. So this whole thing is one orbit, one Hubble orbit. And up to here is the viewing part of the orbit where you can see the target, and then the Earth gets in the way the rest of the time out here. Okay, so here I've laid out my observations into the orbital viewing period. I've got my data readouts. They all work out hidden behind other activities. In this particular case, I'm actually taking some parallel data with the other camera. So down here are my other observations laid out underneath the primary observations. And this is 2 orbits out of 36 orbits I had to lay out. So it's a big job just to write the proposal is my point, just to get the proposal right. And of course, the important part of this is really writing the science justification that you hope will convince the peer review that your project is worth doing. So it's a big job. Okay. But, so there's a nasty little secret behind the scenes here. And that is that each Hubble cycle is typically oversubscribed by a factor of 4 to 6. That is to say, in these examples here, like let's take cycle 19, which is where I got this proposal. There were over 1,000 proposals submitted, and just 200 were accepted, oversubscribed by a factor of 5. So just writing a good proposal is not good enough. You have to get lucky. You have to write something that the TAC thinks is worthwhile above other very good projects, because in every Hubble cycle, good science gets left on the table because there just simply isn't enough observing time. Okay? So this is what really happens, all right? Here's my beautiful idea. I write my proposal, I submit it, and it comes to the final selection, and they say, no, how can they say that? Well, they did. Okay, so you get feedback from the TAC. You come back the next cycle, the next year, okay, and try again. Sometimes you take that feedback and you revise your proposal, and you try again, and you keep going until you either give up or you write a good enough proposal and it gets over the hump. Okay? So, here's where I tried first. Cycle 15 back in 2006. I was really focused on the young supernova remnants. That's where I started with this process. Was not accepted. So I tried again the next year. Now I got some collaborators that were interested in the stellar populations and the stellar part of the data set, not just the emission line part of the data set. Okay, and we thought we'd put those together and have a stronger proposal, which we did. Nope, didn't get it that time. The next year we decided to try something a little different, because since we did want Chandra time as well, and a lot of Chandra time, this proposal was for 700,000 seconds of Chandra time to observe M83, and then we asked for the Hubble time as part of the Chandra time. They have a joint allocation where you can ask for both that way. That was close but no cigar. They liked that a lot, but we didn't make it over the hump. So we came back the next year and tried again. And this time we decided to break them apart again and go after the Chandra time separately. In the Chandra time, it wasn't just the supernova remnants, it was X-ray binaries, it was the diffuse X-ray gas. There were a lot of different kinds of science in that. So we broke that off, and that time we actually got the Chandra time, but we didn't get the Hubble time. Now this time, these were all ACS camera, and this was before the U.S.A. camera was installed in the telescope, but it was the first year that they said you could propose for it, because after it was installed, that would be the observing cycle. So we tried to get WIF-C 3. We did not get it, but in the meantime, those two fields that I showed you in the yellow boxes early on were taken by the WIF-C 3 team, and analyzing those data helped us to convince them in the next year to give us the time. So we got it in cycle 19, and we were delighted to get that 36 orbits of prime time and 36 orbits in parallel with the ACS camera. That's a long haul. That's 5 years of effort just to get the proposal accepted. Now, you don't know me. I could have written crummy proposals. I'll tell you I didn't write a crummy proposal, but that's because of this oversubscription factor. A lot of good things get left on the table every time through the process. Okay, well, I got an accepted proposal. Now what happens? Well, a lot more work, as it turns out. So in this chart, this is kind of the process that we've been talking about, the peer review, the director accepts it, and we've got an accepted proposal. And well, what happens? Well, we come back, we do not pass go, and we start all over again in what's called a phase 2 process. That's where I have to write the actual details of the observing plan into a file that is submitted. I have to do a grant if you want to get money to support a student or whatever. Once that's submitted, then the people here have to go through a process of cleaning up that proposal and whatnot, which oftentimes involves iteration back with the user to clear things up. We build a long-range plan, this full year plan, where they check for guide star availability, other observing constraints. Any constraints that I've put in the proposal all go into figuring out when in the year it can be observed. We peel off these 1 week at a time to do the weekly schedules, and we get the commands ready to go up. Each of these boxes here is 15, 20 people working full time to do this, right? So it's a lot of effort to make this happen. All right, the commands go up to the telescope and we take data, and that's a red letter day. But then we have to get the data down to the ground, and for Hubble, it actually comes through the tracking and data relay satellite system. It comes down to White Sands ground station in New Mexico. It gets shipped to Goddard Space Flight Center, and it finally makes its way to the Institute, where it enters into this process. Now, I won't go into detail, but again, basically what's going on here is the data processing and calibration step, and then the archiving and distribution steps over here. This involves many databases. There's engineering database, there's the data processing parameters that go into the science data processing, calibration, and so forth. Then the data gets put to the archive, and it gets obviously, there's big databases that have to run the whole archival process and stuff as well. The part of this process that the user sees is just right there. It's like I get a message that says data are available. I say, okay, give me the data, stage it, it's ready, okay, I download it. I come as a proposer. By the way, they actually modeled this after me. Do you see that? But I don't know, you'd think a high-class telescope would have a higher quality icon than that, but anyway, that's what we got. Anyway, you see, I finally got my data, and so I can do something with it. Well, maybe you can understand now why it takes so many people to operate a space telescope. There are just so many things behind the scenes that make this all happen, not only for the scientist and his or her collaborators, but for the data processing and the whole system for planning and scheduling as well. This was back after the last servicing mission. The astronauts came to visit. And so some of these are family members, but there are hundreds of people that work on Hubble that make all that happen. Okay, well, I've got data. Now what? Well, the data comes through as individual files of each of the exposures that was done, and to stitch it together into the data sets that I need to do my analysis takes a lot of work. We have to line everything up on a coordinate system. It's called astrometry. We have to build these big mosaic images that you saw. We have to measure the stars and the star clusters and all those different continuum bands to get their colors and their properties, their sizes. For my emission line stuff for the supernova remnants, I have to actually scale and subtract the residual starlight to get pure emission line images to find the supernova remnants. And then finally, I can actually do what I really wanted to do, which is to search those data and find the supernova remnants. Okay, once I found the supernova remnants, then I have to actually try to get the relevant information out of those as well, including the sizes of the objects, the fluxes, and the different emission lines, and so forth, so I could do the rest of the analysis. And then if you want to compare to other things like Chandra data and whatnot, it happens after all that other work. So I wanted to give you a little sense for what we found. I can't spend a lot of time on that. I could spend a whole talk on that. But basically, we found a lot of supernova remnants. The green circles there on the left-hand side are the supernova remnants that were found in combination between Hubble and our ground-based survey, because you can see some of them are outside the Hubble footprint there. But all the ones inside the yellow box, we were able to measure their sizes and quantify their properties with the Hubble data set. And over here, I'm actually showing you the Chandra X-ray data on the same scale. Of course, it doesn't have the same resolution as ground-based or even as Hubble, but it's pretty good. You see a lot of point sources in here. A lot of those are X-ray binaries in M83. Some of them are background sources. There are little red dots every once in a while. Many of those are actually supernova remnants that show up in the red part of the X-ray band here that I'm showing, the relatively low-energy X-rays. But also look at the diffuse gas that just fills the spiral arms and basically just kind of follows where you have a lot of supernova remnants. You've got a lot of diffuse X-ray emission as well. We're actually energizing the interstellar medium of that galaxy by all the supernovae that have happened over tens of thousands of years. And that whole, you wouldn't know this if I didn't tell you, that is the brightest diffuse X-ray emission in any galaxy that we've ever observed. And it's because of all that supernova activity. Okay, so I just wanted to show a close-up view of a few of these to give you an idea of what the Hubble resolution does for us. Now this is that infrared band I was showing you before. Here's the emission line data from Hubble. Here's the starlight from Hubble. And then here's the Chandra X-ray data over here. Typically in the X-ray they show this red color in this display. Those are relatively low energy or soft X-rays we call them. But this one object here, this kind of very young one, has a very different character to its X-ray emission compared to the others. And it turns out to be the smallest of the three that I'm showing you here. It's the youngest one that we're looking at here. But you also see that it is kind of projected against this band of dust. And part of that coloration change may just be because it's behind the dust. Part of it may be there might be a young pulsar, like a Crab Nebula type thing going on in this very young object, and it changes the character of the X-ray emission. This one here is a middle-aged one that you can see is actually resolved out into a little expanding shell. This one's in between the other two. It's a fairly young one, but you see it's projected right against a cluster of stars, and by looking at the properties of those stars, we can say that the star that exploded here was probably more than 15 solar masses before it exploded. So combining all these data sets in this way, you can start to piece together the answers to some of those questions that I initially wanted to answer. Well, we got to the publication. We actually did it. It was in 2014 June. It was in 2006 when I first proposed for it. So that's a long time to get a science result out. And what else did we do with the data? Well, we actually ran an education and outreach program. It's called a citizen science project on the star cluster population in M83. My friend Brad Whitmore at the Institute here kind of headlined the preparation of this or whatever. And the idea was that just by visually inspecting what the clusters of stars look like, you can actually do a crude age dating of the cluster. And by looking at 2,600 clusters and having citizen scientists, people like yourself, come online and look at these images and classify them according to this kind of a scale, we were able to amass a huge classification and age distribution of the star clusters in M83 without having to look at all 2,600 clusters ourselves to make that determination. But here you can see very young clusters, only 3 million years old, are embedded in H-alpha emission from the gas. It starts to blow it away, so that's a little bit older. Here it's in the process of blowing it away, so it's a little older still. Now the gas is gone, but we still have lots of blue stars, and you kind of resolve some of the structures there. And then as those more massive stars go away, you get just a fuzzy ball that's extended more than a point source and then the color becomes redder as it ages out to, in this case, it's out to 500 million years old. So that was just, the other side of the project, not the supernova remnants. We're involved in a lot of the cluster work. We've gone to a lot of work to put together these mosaics, and so we delivered them to the Mass Archive as what's called a high-level science product. And that was partly so that other astronomers could come and use the data as a starting point for their own work without having to do all that background work to make the mosaics and align the different fields and so forth and so on. And apparently this worked, because here's a list of the articles that have used the data set that I got for my program. Only a few of these are actually by me or by one of my close collaborators. Most of these are by other people that found that data useful for their own science projects. So it was definitely a worthwhile thing to do once we got the data. There's actually a whole nother set of articles that were written on those first two fields of data, or on our reprocessed versions of them when we combined it with our more extensive study. And so these articles, as well as the other articles, all came out of that data set. And quite frankly, I have 3 or 4 active projects that are still going on with different collaborators on various aspects of this data set. So that's quite a story behind one of those pictures on the first page of our presentation here today. I want to just give you a little heads up on one other thing that we found that was a complete surprise, and it combined our X-ray data with the Hubble data in a fascinating way. Hubble had actually looked at M83 back in the year 2000. I'm sorry, Chandra had looked at it in the X-rays here. That's the starburst nucleus. Here's the one spiral arm coming out. And out here in the middle is nothing. But in 2010 and 2011, when we observed, there is the brightest point X-ray source, except for the nucleus has got a bunch of stuff in here, but that's the brightest source in the galaxy, and yet there was nothing there back in the year 2000. So we went and looked at the Hubble data that were taken as part of the initial early release science result, and this is what this is now zoomed way into that, just a tiny, in the center of that yellow box now, we're looking at the Hubble data. Here's a few red stars, nothing very interesting going on, and right in the center here, those white tick marks, is where the position of the X-ray source was supposed to be. And so we said, well, this was 2000 and that was 2010. What if it just went off recently? So why don't we look at it again? So in 2011, we went back with Hubble and looked at it again, and sure enough, there's a blue source right at the X-ray position. And that blue light is coming from a binary star around a black hole, and material pulled off the star must have just gotten close enough that it started to pull material in, and as it swirls in, it heats up, and that UV and optical blue light is what we're seeing in the Hubble data. Complete surprise to us. This is called an ultra-luminous X-ray source, ULX, because of its brightness in the X-rays. And it's fascinating because we've seen these things before in other galaxies, but we've never seen one before it got bright. And so people look at this and they say, it's a blue star, because we see blue light. It's the blue star here that's sending material over onto the black hole. We say, no, there's no blue source there. It's only blue after it starts to accrete the material. We're seeing the actual accretion disk here in the blue light that Hubble sees. So that was a neat little side light. And of course, we participated in the Hubble Heritage release for this. If you actually go to the Hubble Heritage page and go into some of the supplemental information, you can actually pull up a version of this picture that allows you to zoom into it and pan around. It's really quite spectacular. A lot of fun to do that, and there's some other materials that were put together for each of these Heritage releases. It's a fabulous resource out there. So just to kind of close things out, we found lots of supernova remnants. We actually did not find many that looked like what we expected. I didn't have time to really talk about that tonight, but we did. I did show you how the supernova remnants are actually energizing the entire interstellar medium and the spiral arms of this galaxy in a big way. We are looking at the stars nearby to determine the masses of the precursor stars in many cases, many more cases than were available before. And interestingly enough, when the next supernova goes off in M83, we're going to be able to look back at these data and find the star before it blew up and know what kind of star it was directly by observing the precursor star. And of course, I hope you got an indication that it really does take tremendous dedication, effort, and the talents of many people here at the Institute to make results like this possible. Now, I'm probably dating myself by showing this, but every picture tells a story, don't it? And think of all the other stories we could tell. Thanks for listening. Yep.
How many hours do you work a week?
How many hours do I work a week? It depends on what you call work. Some of this is so fun, you know, I can't chalk it up to work. It is a challenge for me to do the research side of my job because really I get very little support money to do that side of my job. I get support money to do the functional role of trying to
Explain how, you know, the astronomers are set up here in terms of what they do in terms of their functional versus their scientific work.
Yeah, so a lot of the science staff here are on 50-50 positions, 50% their own research time or whatever activities they want to do, and 50% support work. Others are on an 80-20, 80% functional, 20% support, although if they get grant money, they can buy more of their time back to work on research. So it's always a balance of finding the functional versus the science. I'm in yet another category since I'm actually a Hopkins person that's working on a contract over here. I have to fulfill the contract obligations. So 85% of a 40-hour week I have to spend on functional work. 15 hours for research is not very much. And so what I end up doing is doing research on my own time. And the hours do go above 40 pretty regularly to actually do this. But I mean, that's the fun part, right? That's the fun. I mean, it's fun to enable these telescopes to do stuff as well. I don't mean that the functional part's not fun, but obviously I got to do astronomy because I love the science and the things that I want to learn about the universe. And that oftentimes takes a back seat, but I try to work it in wherever I can.
Okay, we have a microphone for asking the questions, so Grant will. This one can be tossed. Okay.
Yeah, you can actually toss it, and
Yes.
but you have to speak right into the black.
So for something like yours, you were looking at M83, you knew what you were looking at. How do you calculate exposure time and that kind of thing for something like the deep sky photograph where they really weren't sure what they were going to get?
Well, that one was easy. They had to go as deep as they could go, so they just cranked. They were looking for the faintest things, and so we just said, we'll just give it all we got and see what we can do. Now, it's more complicated than that. You look at the way the detectors are affected by noise and whatnot, and you have to scale your exposure times properly to get the highest sensitivity out of them and whatnot. There's work involved, but basically you just want to crank and crank and crank and add the data all together at the end to go as deep as you can. But for other things, especially if they're optical, where you have data from a ground-based telescope, you can estimate the flux levels, and then you scale the exposure times off of the flux levels that you expect to see. Right behind you.
First of all, thank you. This was absolutely exciting and beautifully done. What is the relationship of Barbara Mikulski with the archives?
Well, Barbara Mikulski has a long-time association with the Institute and with NASA. Of course, she's been a tremendous booster of NASA over the years. And when she was still a senator, she, for the servicing missions and for all the way back to the Hubble launch and the disaster with the Hubble mirror problem and stuff back when we launched, Barbara was there through that whole process. She was supportive. She was firm with the problem that happened and needing to fix it and whatnot. But once it was fixed, she was one of our biggest cheerleaders. She lives in Baltimore. She comes to our Halloween parties. So we have a relationship with Barbara, and she has been a cheerleader for NASA. She's been a cheerleader for the Institute and for Hubble all these years. And as she was retiring from her public life, the archive here was named in her honor.
That's great. Thank you.
It used to be called the Multi-Mission Archive for Space Telescopes, MAST, and so we just changed it to Mikulski.
All right, pass the microphone back to the.
I think she dressed up as the solar system last year.
Yeah.
So you said that the scientists have to come here to do the science because the data is not distributed?
No, sorry. The scientists come here for the peer review process. They sit in rooms of about 10 people by science topic, and they take a batch of the proposals that have been put in, and the scientists on the panel read those proposals, they grade them, they rank them, and then it's the top section from each of those panels in all the different science categories that are accepted for the next round of observing.
And Bill,
So it's the peer review of the proposals where we bring people in. The data go to the archive, and then anybody all over the world could come and get the data out of the archive as soon as it becomes public.
Okay, because I guess that's where I was getting confused, because it said the scientist has to get the data, it's not distributed, but there is
Well,
still access.
You have to come to the archive and get your data when it's ready. They don't send you a CD-ROM or anything like that with the data on it. You have to just come download it
but
yourself.
everything's done
Sorry.
over the internet. Now, there was a question about the peer review, and can you explain how that the peer review is blind now?
Yeah, so this has actually been a big change this last cycle. It's a pain in the butt, actually. But there's been a big motion in astronomy to try to get fairness into the proposal process. Fairness in terms of gender, in terms of age distribution, in terms of all these things. And when you see somebody's name on a proposal, and if it's an established scientist as opposed to some postdoc that you've never heard of or whatever, it doesn't matter if that postdoc proposal reads great and is wonderful, you already have an implicit bias toward somebody that's an established scientist, right? Or whatever the case may be. So this cycle, they said, you don't even refer to your own work in your proposal and say, and I, Blair et al. 2014, did blah, blah, blah. No, you take the I part out of this. You basically make the whole referencing in your proposal anonymous. The names, although they're on the proposal when it's submitted, are not given to the peer reviewers. So the peer reviewers are looking at a proposal with none of that ancillary information that might unintentionally bias their judgment about the proposals. And it really focuses the panel on looking at the science description that's provided and making their judgments for the best science based on that.
And I was impressed that, even after all these cycles that we've done, and we got incredible science out of Hubble, we're still working to improve the process.
Yeah.
Which was very impressive.
And the web process will build off of the Hubble process, all those years of experience. Now when web starts accepting proposals, it's going to learn from those experiences.
Okay, question up there.
So I had a question kind of about the process, thinking about those 1,000 proposals, they get kind of winnowed down to 200. I wonder, do you have a better chance if you're kind of lucky and maybe 2 or 3 proposals want to look at the same thing? I mean, does that happen where they could, just to use the time on Hubble more efficiently, maybe those proposals would be more accepted than ones that are more disparate?
There are so many variables in the process that was probably one variable, but there are many, many other things that come into the process. And it really comes down to things like which panel does your proposal go to, and is there somebody that happened to be on that panel that kind of understands your science and wanted to advocate for it in the panel if they really liked. I mean, so there are a lot of intangibles as well as writing a good proposal and supporting it as best you can at the beginning. So there's a lot of things involved in the process. Yeah.
Just a very simple question though. With the recent gyroscope failure in recovery, were there any long-term ramifications for the proposal cycle?
Well, since they recovered and now they're still operating with their 3 gyro mode, there's very little impact. I think one of the reasons that the announcements of this last cycle were a little bit slow in coming out is they really wanted to understand where they were with this gyro problem. Gyroscopes are an interesting thing. We had gyro problems and reaction wheel problems on the Fuse satellite that I ran over at Hopkins for many years as well. And it's amazing how with software and other tricks, these engineers figure out things to do to keep these satellites running. For Hubble, the gyroscopes are sensors. They are sensing motion, relative motion, and feeding that into the pointing system, which is actually done by what's called reaction wheels, momentum wheels that are spinning and change the rate of speed to move the satellite around or to hold it steady. So it's a sensor problem. And when you have 3 gyros, you're getting information on all 3 axes from the gyroscopes. Everything's happy. The control system is happy. When you drop below 3 gyros, things change. All of a sudden, you've got to find some information from someplace else, where they substitute in star trackers for pointing motion, that their job is to sense the stars, not to hold the satellite steady, but they can change the software to use star trackers to take place of the gyros. And they can actually operate with one gyro and the star trackers and work almost as good. They just have certain limitations on when they can point to various places around the sky. But they basically can still see the entire sky. It's just a matter of they have to be a little more careful about when they go to a certain part of the sky to observe with one gyro mode. So they're working with 3 gyros now. It's the last 3 out of 6 that are working right now. So when they lose another one, they're not going to go on 2 gyros. They're going to drop to 1 gyro, use that one till it dies, and then use the last gyro until it dies, and extend the lifetime of Hubble as far as they can. And so there will be some restrictions to the pointing when it gets down to the 1 gyro.
And pertinent to your question was that the 3 weeks of scheduling that they'd already planned for those 3 weeks will get folded into the later scheduling. Okay, the folks down the scheduling branch, whenever there's a safe mode, they have to readjust, and they've been doing that for years. I mean, it started off like it was 60 days they uploaded commands in advance, and now it's down to a week in advance.
Yep.
So that has been amazing, the amount of improvement they've done in the how long time advance they need to schedule Hubble. Other questions? A question over there and one down front.
Ready? Sure.
That's great, isn't it, that microphone? You throw it around.
This is the coolest thing ever. So you mentioned that you had 4 days of observation time for your M83 research, which sounds like it's more than maybe your average or fair share. I don't know if you maybe you can talk a little bit about what is more of a typical observation that you get as...
There's a distribution of proposal sizes that go from a single orbit or 2 up to hundreds of orbits for the large and very large projects that are they're graded as sort of a separate entity because they do take so much resource. They have to really be whiz bang science like deep field or those kind of things, to get the major or exoplanets get a lot of time somehow. I don't know why. But anyway, so I mean, what's typical? I don't know. There's a range. This would have been classified as a medium proposal, and it is difficult to get that kind of intermediate size proposal. 30, 50, 60 orbits are difficult to get because it is a sizable chunk of time, but it's not like the big program. So it's in between there someplace. Many of my proposals in the past have been of order 5 to 10 orbits. That's probably a little more typical for many astronomers proposing in. They have a specific thing that they want to do. This would, if this galaxy was smaller and it didn't have as many fields to cover the main body of the galaxy, it wouldn't have been as many orbits. It's just which object do you want to observe and how many fields do you need and that kind of thing. Yeah.
Thank you.
Okay, we had a question down here.
You want to speak real loud, or I can voice it over again. Or you can wait for the mic.
We'll wait for it.
We want the online audience.
Here it comes.
Yeah.
The James Webb hasn't seen first light yet, hasn't been launched, but I presume you already have a long list of requests for observation time.
So interestingly enough, the Webb telescope, I'm sure you heard in a previous month or you read, its launch was delayed. It was supposed to be about now, not that long ago, and it got pushed off and is now sitting out in early 2021, which is a long time in the future. But before that launch slip happened, we were actually in the first proposal cycle for the James Webb telescope. We had not gotten to the submission point yet. We were 10 days out from submission, but people in the community were working on proposals, and they announced the initial launch delay at such time that they decided to just hold the proposal cycle and not let those proposals come in. Interestingly enough, what we did in response to that was we immediately contacted the community and got feedback on the tools that we had in place to support them for that initial cycle, and we got lots of feedback for making the system better when we actually do this for the first time for real, which will be the proposal opportunity right now is scheduled to open up next December, a year from now. The first call for proposals, and the proposals would be due then in spring or summer of 2020 for the first cycle.
We have a question from online. Let's see. I wonder if anyone has ever calculated the person hours per HST exposure. In other words, the hours of the STScI staff divided by, like for a full year, divided by the number of exposures in a year. So how many person hours go into one of these observations? The astronomer has to put all those person hours, but all the people behind the scenes.
Wow.
It's a large enterprise. I
I could say it's a large enterprise, and I cannot even begin to fathom a number. Maybe a Google or something? Maybe on exposure, of course, some exposures are long and some are short, so I don't know exactly what the criterion would be, but it's an interesting question to try to.
We've got about 500 people on average working here, and we do 3,000 orbits of observations per year, right? If we consider
Yeah, you could
exposure, so something like that.
Yeah.
500 years divided by 3,000 orbits. Okay.
It's too much math.
My turn?
Yeah.
There's an object that orbits our sun about once every 400 years. I believe it's K2, recently discovered. What can you tell us about that? Oops.
K2 is the Kepler-2 mission. Is there?
I haven't heard of anything called K2. I mean, if it's
Is this the Planet 9 thing? It's not. No.
I heard it probably through the people at. I heard it through the people maybe over at the people in Columbia at their meetings, and they're talking about 400 years to go around. So there's something as big, and it goes around our sun every 400 years.
Isn't the planet the large Kuiper Belt object that I discussed last month during the news?
It might be. I mean, Pluto takes 230 years.
239 years for Pluto.
So
right?
it's not that much farther out than Pluto, but
400 years is
Way out there, yeah.
it's not that far out there.
And there's,
You can compare it to the Oort cloud and everything.
Instead of even though it's
Actually,
close to
the object I discussed last month was over 700 years in its orbit.
it may do something with our weather on Earth, is what they were thinking.
Nah, I don't think so.
Okay.
Okay.
actually, so so January 1st coming right up, the New Horizons mission, the thing that flew by Pluto, is going to fly by another object that's farther out on January 1st, coming right up. And that object has a Hubble connection, right? Because they found the thing to look at by taking deep Hubble pictures in the direction where New Horizons was headed, and said, is there anything out there for us to look at? They didn't know what they were going to be able to fly by. And they found two candidates. This was the better of the two candidates, and it was within the window where New Horizons could adjust its path to fly by this thing. And we have no idea. It's just a little fleck of stuff out there in the Kuiper Belt, but we're going to go see another Kuiper Belt object.
Tiny little nothing, but it's been given the impressive nickname of Ultima Thule. It's actually catalog number MU69 or something like that, but Ultima Thule. All right, do we have one more question? Yep, go ahead.
What was astro drizzle?
I got rid of most of the buzzwords, but a few, I grabbed slides from other talks and stuff, so sorry about that. Astro Drizzle is an incredible but complicated piece of software that allows you, if you've taken your data in the proper way, to combine data sets in such a way that you actually improve the resolution above and beyond the initial pixel size of the camera. So imagine if you have little square pixels of a CCD array, and you take a picture and then you offset by a fraction of a pixel and take another picture, and a fraction of a pixel and take another picture. When you stitch all those data together, you can actually, with software, create an image that has better resolution than any of the individual pictures. Astro Drizzle does that. It's also the thing that does a lot of the aligning of separate exposures so you can add them together. And as you do that, then you can get rid of bad pixels and cosmic rays and things that are not real data in your data. But Astro Drizzle is an important thing for getting the absolute highest quality imaging out of Hubble.
All right, so that will be our event for this evening. There will not be any observing tonight. Next month, in December, Mark Kamiankowski will be talking about black holes and other dark matters. Please join us, and let's give Bill one more round of applause. professionals as astronomers. We don't just sort of like come up with an idea. 6 guys. What about this? You know, somebody asked me, like, I said, well, just watch